Hey folks, my name is Namit and this is my thrust vector control system and I'm going to tell you all about it. To start off, a thrust vector control system is a rocket engine mounted onto a 2-axis gimbal used to control the stability of a rocket. It works like this: when a rocket is launched, it's bound to deviate from going in a straight path because of outside forces. So when the rocket begins to tilt in one direction, the thrust vector control gimbal redirects the thrust in the opposite direction to correct the rocket angle. So, how do we build it? Well, to start off, we need a mode to measure the angle of the rocket. To do this, I use the MPU 6050 inertial measurement module, which gives you accelerometer and gyroscopic data. Using this chip, I can read the pitch and roll angles of the rocket. Aside from that, we need a mode to control the rocket engine as well as the flight data. I'll come back to that, but right now, let's take a look at the design. Once the design was completed, the next step was to 3D print the components and assemble them together. And one of the most important parts of this system is the control software. To control the angle of the rocket, I have designed a PID controller. PID stands for Proportional Integral Derivative, and it is a closed-loop control system that enables you to regain stability of a system by multiplying our reaction angle by certain gains. The proportional term takes into account the error of the rocket angle, the integral takes into account the cumulative error, and the derivative term takes into account the rate of change of the rocket angle, which ensures that we don't overshoot the rocket engine. So for the rocket engine, I decided to use the C63 solid rocket motors. They generate about 15 newtons of thrust and has a burn time of 2 seconds. Prior to this project, I had never used a rocket motor, so I thought the best way to test this engine was to do a static fire. To do this, I designed the engine mount that holds down the motor in one place. It was a quick and easy design, so here's how that turned out. So everything is good to go, but we need a way to save the flight data. For this, I used the SD card module that can save data directly from my Arduino, allowing me to have a mode to review how the system performed during its launch. So everything's ready to go. The last step was to fire the rocket engine. That was fun, so let's take a look at the flight data. Alright, so I've imported the flight data into an Excel sheet, and it's important to note that during the flight I actually only thrust vectored on the pitch axis because the roll axis servo was not working properly, so I locked that in and turned it off because it's dangerous to launch if it's not working correctly. So here we can see that the rocket launches right here, it ignites, and the pitch angle drops dramatically to about negative 55 degrees, and we can see from there it tries to correct itself. As we can see it increasing, tries to get to that 0 degree line, but it actually doesn't. But this tells us that the thrust vector control is working, it's just not as effective. And then after that rocket engine stops firing, it goes all the way back up to about positive 20 degrees and finishes off. And so this tells us that the thrust vector control system on the pitch axis needs a lot more improvement. My next steps are to fine-tune the flight control software, create a recovery system, and fly the rocket. I would love to create a propulsive landing system using this technology, and I'm one step closer to achieving that.